All right, welcome back. This is the review for Chapter 4 and Chapter 10. So there were some questions that were asked, so let's dive into it and take a look. The first thing that was asked was to explain the domain and the range. This isn't like question 1 or anything. I don't know why I wrote that, but the domain and the range of functions like e to the x and say g of x equals e to the x plus 7, or e to the 2x plus 7. Okay. So let's look at this first one first. Let's look at e to the x. You should know what e to the x looks like. You should be able to graph it. So I'm going to get rid of this for a minute. And we're just going to graph e to the x. And we should know that it comes asymptotically off of the x-axis from the left, and then goes through, unless it's been transformed some way, it goes through the point 0, 1, and then exponentially rises, right? So this is e to the x. The domain is all x values that I could plug in there, and I can plug anything in there. All of these positive numbers, all of these negative numbers, any of these real numbers I can plug in there. So for e to the x, my domain is all real numbers. It's everything. Everything from negative infinity, including 0, all the way up to infinity, right? The range, though, stops here at this asymptote, or starts there, if you will, but it doesn't have this line is never actually going to get to 0. It'll get close and close and close and arbitrarily close. And so I would say that the range of this thing starts, but is not including 0. But then it goes up, and it goes up forever, so it goes to infinity. And infinity, of course, not a real number, is never included, so it's open on the other side. All right, that's e to the x. The other function was e to the 2x plus 7, right? So let's think about what e to the 2x plus 7 does. Well, if I multiply this number up here by 2, what that really is doing is just kind of shrinking my exponential in the x direction. It's a shrink by a factor of 1/2. And so really all that does is kind of crams it in, shrinks it this way. But this plus 7 is really what happened, what is interesting. Because if I didn't have that, the domain and the range don't change, right? I can still plug any x value in there. I'm still going to get any positive y value out of it. But this plus 7 takes everything and moves it up by 7, including this asymptote. So instead of going, say, through here, we would go 1, 2, 3, 4. Maybe I need to rescale this. It's moved up by 7 to go through 0, 8. The asymptote moves up by 7. And so I asymptotically leave that line, go through, and then increase. So you can see the domain is not affected. I can still plug in any x value in here, double it, and then take e to that power. So all real numbers for my domain is still the case. What happens to the range, though? Now I'm not going to hit these numbers between 0 and 7. And so I start at 7, and I go forever upwards. So the range has changed. It is from 7 to infinity, and of course opens on both. Because we asymptotically are approaching 7 now, we don't actually ever get there. Good. Okay. The next question that was asked was about the Gaussian elimination. Now, if it's me solving these, I use Gauss-Jordan elimination because Jordan just came in and said, hey Gauss, why did you stop there? Let's just keep going and finish it off. But let's look at this one. I've got x plus 2y plus 5. Z, 5z, equals 9. And I'm assuming this has come from the study guide. If it's not, then it's just a problem. But 2x plus 3y and minus 4, I'm assuming that's minus 4z. Plus 3y minus 4z equals -9. And 3x plus 6z equals 15. Right. So if I'm going to use Gaussian or Gauss-Jordan elimination, I first want to write this as a matrix. So that is 1, 2, 5, 9. I don't know why my 9 has the hugest tail ever. 2, 3, -4, -9. 3, 0, 6, 15. Right. That's my matrix. And then I want to go through and get the 1 in the upper left and then eliminate everything else in that column. Now, this question specifically says Gaussian elimination, so I'm going to only do the Gaussian part and not the Jordan part. The Gaussian part is to get zeros down in this bottom 3 guys and 1s down the diagonal, right? And then figure out what's happening up there later. Jordan came in and said, well, if you're getting zeros here, why don't you get zeros here as well and just be done with it when you're at the end of your matrix manipulation. So the first thing I want to do is get a 1 here. I already have that, so that step's easy. The next thing I want to do is eliminate the 2 and the 3 here. So I would take -2 row 1 and add it to row 2. And here I would take -3 row 1 and add that to row 3 to get my new rows. Since I'm not playing with row 1, or I'm not changing row 1, I'm just going to rewrite it. Row 2 becomes -2 times 1 is -2 plus 2 is 0. -2 times -2 times 2 is -4 plus 3 is -2. This is math. Math's hard. -2 times 2 is -4 plus 3 is -1. Last time I actually checked. -2 times 5 is -10, and -4 more is -14. And then -2 times 9 is -18, and minus 9 more is -27. Okay. That's my row 2. Row 3 is -3 row 1s plus row 3, so -3 and 3 is 0. -6 and 0 is -6. -15 and 6 is 9. -9. And then -3 times 9 is -27, plus 15 would give me -12. The next thing I want is this to be a 1, and that's easy just by multiplying by -1. So I get 1, 2, 5, 9 still in row 1. Row 3 is still 0, -6, -9, -12. And then multiplying the middle by a negative goes 0, +1, +14, and +27. Now, again, if I were doing Gauss-Jordan elimination, I would use this 1 to eliminate the 2 and the -6. I'm specifically doing only Gaussian elimination, so I'm going to eliminate this -6 and leave the 2 alone. So that is to say, I'm going to take 6 row 2s and add it to row 3. This gives me 1, 2, 5, 9. 0, 1, 14, and 27. 6 of these is 6, and negative 6 gives me 0. 6 times 14 is 84. Minus 9 is 75. Okay. And then 6 times 27 is 81, 92. 81 times, not 80, let's see, 162. Yep, and then minus 12 gives me positive 150. Okay. All right, so the last thing that I want to do for Gaussian elimination is divide the bottom by 75. Leave the others alone, and when I get to this point, my Gaussian part is done. Dividing the bottom by 75 gives me 0, 0, 1, and 2. And then I have the middle and the top row unchanged. And again, I don't like this. I think Gauss, I don't know, maybe he got lazy, but it's easier for me to think about just clearing the whole thing and doing the Gauss-Jordan elimination, but too late. Here we are, we have z is equal to 2. Okay. I know that. What I also know, though, is that if I go back, I'm going to get rid of all of this, but if I go back into the previous equations here, and just resubstitute, this second equation tells me that y plus 14z is equal to 27. But I know what z is 2, so if I say y plus 14 times 2 is equal to 27. 14 times 2 is 28. And then I just subtract 28 to solve for y. So I know y is negative 1, z is 2. I also have one last equation that has an x in it. This tells me that x plus 2y plus 5z is equal to 9. But y is negative 1, so this is then x plus 2 times negative 1 plus 5 times z, which is 2, should equal 9. All right. That is to say x minus 2 plus 10 should equal 9. This is altogether an 8. So if I subtract 8 from both sides, then I get x is equal to 1. And I have it. I have my solution. X is 1, y is negative 1, z is 2. Solved. Done. All right, the next one is an inverse. So 1, 2, 5, 3, negative 1, 1, and 1, 2, negative 3. We're trying to find the inverse of this matrix. Right. So what I would do here is augment this with that identity, 1, 0, 0, 0, 1, 0, 0, 0, 1, and then go through the reduced row echelon form to get the 1s down the diagonal and 0s everywhere else. I'm in luck. There's a 1 in my first spot already anyway, so I don't have to do much there. I'm going to eliminate the 3 and the 1. And I'll do that by using that 1, so negative 3 row 1 added to row 2, and then just negative row 1 added to row 3. Or you can do row 1 minus row 3, it doesn't matter. Right? If I do this, let me lower myself. I tend to go higher and higher as I go. Row 1's not being messed with, so 1, 2, 5, 1, 0, 0. Negative 3 row 1 plus row 2, so negative 3 plus 3 is 0. Negative 6 and negative 1 more is negative 7. Negative 15 and 1 is negative 14. And then negative 3 and 0 is negative 3. Negative 3 times 0 is 0, plus 1 is 1, and 0 and 0. Okay, so for the bottom one, negative row 1 plus row 3, so negative 1 plus 1 is 0. Negative 2 and 2 is 0, that's kind of nice. Negative 5 and negative 3 is negative 8. Okay. Negative 1 and 0 is negative 1. 0 and 0 is 0, and 0 and 1 is 1. Okay? Okay. Now, this one's a little bit weird because it's hard to get this negative 7 to be a 1 because I can't mess with the row below it because it's already at a 0. I can't say, oh, multiply the bottom row by something and add it to the top and get that 1. But I also can't mess with the one above it because if I do, I'm going to F up that first X column, right? And I don't want to do that, so what I'm going to do is skip this guy and say, I'm going to come back and do this later. Right? I'm just going to move on to the next step, which would be to turn that negative 8 into a 1, which unfortunately means I cannot at this point avoid fractions. I have to deal with it. I'm going to get a fraction there. Right? So I'll do it. I'm going to divide this by negative 8. Right? There's no other way to, there's probably other ways, but I can't avoid fractions at this point. So what do I get? 1, 2, 5, 1, 0, 0 still, 0, negative 7, negative 14, and I could have just decided, well, since I'm going to deal with fractions anyway, I could divide the middle one by negative 7 and just have the fractions there, but it doesn't matter. All right, got that. Dividing the bottom by negative 8 gives me 0, 0, positive 1, positive 1/8, 0, and negative 1/8. I'm going to use this 1 to eliminate the 14 and the 5. Unfortunately, 1/8 will be proliferating through the rest of my matrix over here. And so, how do I do it? Well, I go negative 5 row 3's added to row 1. And then I do 14 row 3's added to row 2. And I don't change row 3. In fact, row 3 is done, never being changed, so I know my final answer has fractions. And it's going to have fractions all over it because they're about to get shoved up. 0, 0, 1, 1/8, 0, negative 1/8. Negative 5 row 3's plus row 1 gives me 0 plus 1 is 1. 0 plus 2 is 2. Negative 5 plus 5 is 0. Negative 5/8 plus 1, or plus 8/8 is 3/8. Negative 5 times 0 is 0, plus 0 is 0. Negative 5 times 1/8, negative 8 is a positive 5/8, plus 0 is 5/8. Okay. The middle one, 14 row 3 is added to row 2, so 14 times 0 is 0, plus 0 is 0. 14 times 0 is 0, plus negative 7 is negative 7. 14 times, where am I? 1, plus negative 14 is 0, right? 14/8, or 7/4, plus negative 3, or minus 12/4, that's 3, right? Is negative 5/4. 14 times 0 is 0, plus 1 is 1. 14 times negative 1/8 is negative 7/4 plus 0, negative 7/4. Okay. So I'm almost there. The next thing I want to do is I need to get that to be a 1. I only have one option. That's to divide the middle row by negative 1/7. Or multiply it by 1/7. Divide it by negative 7, whatever you however you do it. So the top and bottom are not changed. That gives me 1, 2, 0, 3/8, 0, 5/8. Middle one's all divided by negative 7, so 0, positive 1, 0. I'm dividing this by negative 7, so that goes positive, and 5/28. Not the coolest number ever. Negative 1/7. And positive 1/4. Okay. And then the bottom one, of course, didn't change. 0, 0, 1, 1/8, 0, negative 1/8. And the last thing that I have to do is to get rid of this 2, and I do that with this 1. So that's negative 2 row 2's added to row 1. Everything else is how I want it. And so we get negative 2 times 0 is 0, plus 1 is 1. Negative 2 times 1 is negative 2, plus 2 is 0. Negative 2 times 0 is 0, plus 0 is 0. Negative 2 times 5/8, or sorry, negative 2 times 5/8 is negative 5/14. Right? Plus 3/8. Not the coolest thing you've ever had to do. Common denominator here is 56, unfortunately. So this becomes, I'd have to multiply this by 4. Over 4, that gives me negative 20 over 56. Plus, here I'd have to multiply by 7, so that gives me plus 21 over 56. This is just 1 over 56. Where am I? Okay. Yuck, right? The next guy here, negative 2 times negative 1/7 is a positive 2/7, plus 0 is 2/7. Negative 2 times 1/4 is negative 1/2, plus 5/8 is the same as negative 4/8, plus 5/8. That's 1/8. Yuck, right? The rest of it's the same though, so 0, 1, 0, 0, 0, 1, and then this 5/28, negative 1/7, 1/4, 1/8, 0, negative 1/8. And that's your inverse, is that big bag of ugly on that right-hand side. You might be asking yourself, is there an easier way? Yeah, sort of. There's cofactor expansions, which would be a little bit quicker and easier. But it's outside the scope of this course. So keep going in math. Take linear algebra at some point, Math 2270, and you will be able to do this quicker than I just did it. So, all right. Let's look at a Cramer's rule problem here. Oh, I forgot where I'm at. This is for UNLV. It's not Math 2270. I don't know what it's called at UNLV. I forget. but linear algebra. All right, Kramer's rule, I've got 2x plus y plus 3z. Equals 15 y plus 5z equals 19. This has to be written wrong. I have 3z minus 2z equals negative 2. It's probably 3y minus 2z equals negative 2. Let me maybe pull up the study guide here and see. See if I can find out where this came from. It is an X in the study guide. So everything else looks all right. Okay. And as a note, I'm looking at the last one that we just did, looking for the inverse. That one has half of one of the problems in it. 1, 2, 5, 3, negative 1, 1, but then that bottom row in the question that I was asked says 1, 2, negative 3, but on the study guide it's 2, 0, 3. So hopefully the study guide problem is not nearly as crappy as that one, because that was not the greatest. But at any rate, that's how you would do one like that. But we're looking at this one, we're going to use Kramer's rule, so I want to know what the matrix is. So this is 2, 1, 3, 15, 0 for the x, 1, 5, 19, 3, 0, negative 2, and negative 2. Okay. So what I want to do is find my determinant, and then the determinant of the x matrix, the determinant of the y matrix, the determinant of the z matrix. So let's just clear up a wee bit of room here. The capital D, the determinant, is the determinant of the system 2, 1, 3, 0, 1, 5, 3, 0, negative 2. Just this left hand here. Exploit your zeros if you can. So here I would expand on, and you know what, I'm going to expand on this one because I like those ones sitting there. So remember your positive or negative matrix. This 2 is in the positive spot, so when I start with this 1, it's in a negative spot, so I'm going to change its sign right off the bat. Negative 1 multiplied by what's left if I take out that column and the row, so 0, 5, 3, negative 2. The 1 is back into a plus spot, so plus 1 multiplied by, get rid of the middle row, the middle column, and I have a 2, 3, 3, negative 2. Which is to say then I have negative 1 multiplied by 0 minus 15, so negative 15, plus 1 multiplied by negative 4 minus 9. Or I have positive 15, negative 9 minus 4 is negative 13 times 1. Okay, so I have my determinant is 2. Now the dx is simply taking the determinant of that system that I just erased my numbers I need, 15, 9, and -2, I think, and replacing my x with them. And then everything else here stays the same. 1, 1, 0, 3, 5, -2. Exploit your negatives. So either expand on this column or this row down here. It doesn't matter. I'm going to choose this column because why not? So the 1 is in a negative spot, so -1 multiplied by. If I eliminate that row and that column, I have a 19, 5, -2, -2. This next one is back into a positive spot, so I don't change the sign, so it's +1 multiplied by 15, 3, -2, -2. Or -1 multiplied by 19 times -2 is -38. 5 times -2 is -10, so minus -10 is +10. Plus 1 multiplied by -30 plus 6. So I have -1 multiplied by -28 plus 1 multiplied by -24, or 28 minus 24, which is 4. So far, I know that the determinant was, geez, I hope it was 2. Good thing I erased it. The determinant x is equal to 4, and so I would have dx over d is equal to x. Dx is 4. D was either 2 or -2, I can't remember now, and I erased it like a dummy. But that makes x either positive or -2, depending on whether d was positive or -2. And I'll save the rest of it. The rest of it's the same for the dy. You're just going to replace your y column with your solutions, find the determinant of that, and then divide it by whatever it was that we really got for d, which I think was 2, but it might have been -2. Okay. All right, let's do a partial fraction decomp. There were some ugly ones in the homework. Those ugly ones might pop up in engineering type math, but not going to pop up on a final exam. They're far too time consuming for that. So let's take a look at this one. I have 32 over x plus 3 squared times x minus 5. So for this one, it's important to note that you would end up with a constant over an x plus 3 squared and a constant over an x plus 3. For the same reason as if I had 1 over x plus 1 over x squared, I'm going to end up with something over an x squared, right? We're just kind of looking backwards at how these two things would combine and still end up being over an x squared. Likewise, if this were x plus 3 squared and that were an x plus 3, the common denominator still is x plus 3 squared. And so that's why I have to account for the possibility of having both fractions. And I have an x minus 5, so I have one more constant over an x minus 5. Now, if I multiply by the lowest common denominator, which is x plus 3 squared and x minus 5, I should eliminate my denominator altogether. That's the purpose of what I'm doing here. And it does here, x plus 3 squared cancels the x plus 3 squared, x minus 5 cancels x minus 5, and I'm left with a 32 on the left. On the right, x plus 3 squared cancels with x plus 3 squared, but I'm left with a multiplied by x minus 5. X plus 3 cancels with one of the x plus 3's, but leaves the other one, so I have this b multiplied by x plus 3 multiplied by x minus 5. And then the x minus 5 cancels here, leaving me with c. Am I running out of space? Yeah. Darn it. Wrote too big. And so I'm left with this c multiplied by x plus 3 squared. Now we have that convenient values of x thing that says, hey, what if I come along and say, let x equal 5? Because 5 minus 5 will zero this out. Then I get 32 equals, that's gone, and this is gone as well. 5 minus 5 is gone, so I have 5 plus 3 is 8. Squared is 64. Dividing side by 64, and I get c is equal to 1/2. So that one's not too bad. We found it. The other nice value is what happens when x is negative 3. If x is negative 3, then 32 equals negative 3, so I have negative 8a. But negative 3 plus 3 is 0, so all of this stuff multiplied is 0. Negative 3 plus 3 is 0, squared is 0, times who cares, it's all 0. So divide each side by negative 8, and I have a is equal to negative 4. And I found A and I found C, but I can't use this method to solve for B because I can't eliminate A and C and not eliminate B. It doesn't happen, right? So what do? I'm going to make note of these, write them somewhere else perhaps. A is negative 4, C is 1/2. I want to figure out B, so all I really need to do is go back and use the other method to where we'd end up with the system, but I don't really care about the system so much because it's going to boil down to one unknown, so I only need one equation. So I'll expand some stuff. This is 32 equals ax minus 5a plus this is x squared minus 5x plus 3 more x is minus 2x and then minus 15. And I'm going to take my b and distribute it through there. So I get plus bx squared minus 2bx minus 15b. X plus 3 squared is x squared plus 6x plus 9. And distributing the c through there gives me cx squared plus 6cx plus 9c. Right? And if I get my x squares together, then I'm going to rewrite this as 32 equals bx squared plus cx squared plus, and I don't even care what the rest of this is, I know that b and c have to be the opposite symbols because when I factor out the x squared, that gives me b plus c times x squared. Since there's no other x squareds in here, that has to be equal to 0 because there's not an x squared on the left-hand side. So I have this, b plus c is equal to 0, which if I subtract c from both sides, then b is simply the opposite value of c. I know c, it's 1/2, so b is negative 1/2, and I'm done. That's that, right? I can create a system of 3x3s. I can solve it. I'm going to solve it with a is equal to -4 and c is equal to 1/2. So cut it, make it smaller. I can turn it into one equation. That's all I need because all I need is that one variable. And I did that and I'm done. All right. And that looks like it was the last question that was asked. So hopefully that was helpful. Good luck on your exam, and I'll see you guys for the next one.